Click on. And there we go. Okay. Hello, friends, family, and random internet strangers, and welcome to week 5 of Let's Read Code. So, this week is where things start to get a little more intense and fun, and we actually start doing some stuff. So, started off talking about logic gates in chapter 11, which are basically just repackaging the switches and stuff that we saw last week into nice, happy little things that perform simple logical operations. So we're going to go jump back into Minecraft for a bit to start with. So that mod I was using last week, which I also posted a link to on the website for this thing, also includes logic gates. So this is an AND gate. So if I just turn one of the switches on, nothing happens. But if I turn both of them on, the light lights up. Over here, we've got an OR gate. So if either of them turn on, or both of them on, lights up the light. And over here, we have an XOR gate, exclusive OR, which means if one of them's turned on, the light turns on, but if both of them are on, then the light turns off. So we also saw some variants of these, NAND, NOR, and XNOR, or add a couple other names for it in the book. But basically, it's this, but then inverted. So you stick a NOT at the end of it. So that was basically chapter 11. It just showed you how to put these things together with relays and how to start hooking those all together. So, start of chapter 12, talk about getting these things to start doing math. So, switch here for a second. So, we want to start adding binary numbers together. So there's 4. If we just want to add one binary digit to one binary digit, right? We can do 0 plus 0, 1 plus 0, 0 plus 1, or 1 plus 1. So if we do these things, we get a 0, a 1, a 1, and a 2, right? So if we write this a little bit differently, say we want to build a circuit that has 2 inputs, A and B. For 0, that's a 1, and that's a 1, that, and they're both 1s. So we're going to get 2 outputs. We're going to call the carry and a sum. So the 0 still, that's going to be a 1. Nope, backwards. 1, that's going to be a 0. 0. So if we want to express this in terms of some of these logical operators that we've seen, so our carry is only 1 when both A and B are 1. So that looks an awful lot like an AND. And the sum is only 1 if exactly one of the inputs is 1, which also looks a lot like the exclusive OR of A and B. So I'm going to jump back over here. So right here, I've got a simple 1-bit half adder put together here. So I'm using a rather helpful feature that comes out of this Project Red mod called a bundled cable. So ordinarily, when you run cables next to each other, they, all connect. We have these colored cables that will only connect to color or cables of the same color. And then a bundled cable lets you put a bunch of colored cables into the same block. So this brown over here is connected to that brown and that brown. So when I turn this switch on, it turns on this side of the gate and that side of that gate. So when I turn on either of the inputs, my sum light turns on. When they're both off, everything turns off. And when they're both turned on, the sum light goes out and the carry light comes on. Because again, over here, I've got an XOR gate connected to my sum and an AND gate for my carry. So trying to build this over and over and over and over and over again would get super gross and tedious and unpleasant. So instead of trying to do that, we're going to switch to another lovely piece of software here. Called Logisim. So I stumbled across this several years ago, I think when I was teaching. Basically, it's a logic circuit simulator. So it's full of gates and wiring things and buttons and LEDs and stuff to simulate building logic circuits. So I can drop an AND, drop a dip switch. This is an actual thing. It's just a bunch of little on-off switches inside a tiny box. So I'm going to hook up my two switches to the two inputs on my AND gate. I'm going to wire out the output to this LED. I'm going to grab the finger pokey tool, which actually lets us interact with the circuit. So when I turn on both of the inputs, it's yelling at me about something because something's not actually connected. What did I do? Go there. Why aren't you? That's interesting. Never seen it do that before. You there. You there. Okay, that's better. That was weird. So when I turn either of the switches off or both of them off, the LED goes out, but when they're both on, the thing turns on. So I have pre-assembled a bunch of the stuff that we need to go through what the book has been talking about in the last 2 chapters I had you read. So we'll start off with the half adder, which is the thing we just saw in the Minecraft simulation. So the other cool thing about this software is it lets you build circuits and then use them in other circuits, kind of like we saw in the book, where once he described what a half adder was, it just got replaced with a box labeled half adder. So basically do the same thing here. Over here are the pins, which are how we get circuit or signals in and out of these little sub-circuit doohickeys. So I've got 2 input pins labeled A and B. Each one is wired into, I've got an XOR gate up here and an AND gate down here. And then the outputs are connected to a sum and a carry pin. So I go drop one of these here, hook it up to a switch with LEDs. Once again, see when I turn one of these on, the sum light lights up. Really move that because that looks kind of, oops, nope, not that. Got it. So when one of them's on, the sum light turns on. I turn both of them on, the sum light goes off, and the carry light goes on. So the next step from there, so we have this carry output, but if we want to add, more than one bit together at the same time, kind of need somewhere for it to go. So that's where the half adder circuit comes in. So we've still got our two main inputs as well as this carry in. And then also had our carry out. That is when you OR the carry of the half adders together, you get the carry out. Then when you add your inputs and your carry together, that gets you the sum out of this. So again, if I go drop these in here, around, there you go. There. So once again, only one of my primary inputs is on, then the sum turns on. They both turn on, then my carry out turns on. And then if I turn on my carry in, while both of these things are on, turns the sum on. If I turn one of these off, then the sum turns off, the carry out stays on. Turn them both off, but the carry in is still on, my sum turns back on. Another cool thing about this piece of software that's very helpful when your circuits get big and complicated, you can right click on one of our little sub circuits here, go view, and it will actually show you what's going on inside of it. So right now, all three of my inputs are on, which means this half adder, the sum is off, the carry is on. This half adder, since carry is true, the sum of this other thing is false. So my sum is true, but my carry is false. So my big output sum is on. And because one of these two things is on, my carry output is also on. So that means we can wire 8 of these doohickeys together, create this very large, slightly unwieldy looking thing, and start adding things that look like actual useful numbers together. So the way this works, just like the bundled wire we saw in Minecraft, this thing also lets us bundle multiple wires together into one bigger wire. So here I have an input pin that takes 8 bits worth of stuff. This is a splitter that will split out the 8 individual signals into their own individual wires. Same thing for my B input. So A0 and B0 get wired in to this first full adder. Carry in gets set to 0 because we have nothing to bring from a previous adder. The sum goes out to another splitter, which is really unsplitting the signal, taking all 8 of the sum outputs and putting them out on one big wire. Then the carry gets wired into the carry in to the next full adder, and on and on and on and on 8 times until we get to the last one where the carry out just gets wired into a big carry out pin that we can use to actually do some math. So here I have 2 8-switch dip switches wired in through splitters or unsplitters, again in this case, wired into the A and B in on my 8-bit adder circuit. We got my sum out being split up into the appropriate number of little LEDs, and my carry out is also wired into an LED. So if I want to add, let's say 2 and 5, I get 7, which is the number that you would expect because that's how math works, right? So I can go through and flip a few more of these things, do some more math. But it all basically works as expected. We can even, if I turn all of these on and all of these off, that gets us 255 basically, because that's the most you can represent with 8 binary digits. But since we have this extra carry out digit, I can do a little bit more math, and I add 255 and 2, I get 256 plus 1, 257, which again, that's how the math works out. So, any questions so far? I take that as a no. So, the last chapter of the book that I had you read starts doing funny things with math so we can do subtraction. So I'm gonna kind of skip to the end because it talks about some other weird things we can do, as well as the ones complement system, which nobody really uses because it causes other problems and it's harder to deal with. So we're gonna skip straight to twos complement because it makes slightly more sense and makes things a little bit easier to deal with. So let's start with, let's say we have 4-digit or 4-bit numbers that we're dealing with. So 1, also, I meant to say 3 digits, not 4 digits. Anyway, so the way twos complement works, we kind of fence off the biggest valued bit and use it to indicate whether we've got a positive or a negative number. So if we have a positive number, when our biggest number is 0, the other 2 digits work like normal. So here we've got a 0, 1, 2, 3. When we're negative, we're going to basically invert the other digits, and add 1. So this becomes, in essence, our -1, -2, 3, 4. Because, let's start with -4. So if we invert 0, 0, we get 1, 1. And then if we add 1 to that, we get 1, 0, 0, which is 4, right? So the next one, 0, 1, if we invert that, we get 0. We add 1, 0, 1, 1, which is 3. Or keep going here, becomes 0, 0, 1, which when we add 1, becomes that, which is 2. This, we end up with all zeros. We add 1, we get 1. All right, so does that make sense? Small scale. So if we actually go try and do some math with this, let's say we have 2 minus 3, which we all know should end up being -1, right? So if we do that in our twos complement binary here, we have 2, which is 0, 1, 0. We have -3, which is 1, 0, 1. Add them together. 0 and 1 is 1, 1 and 0 is 1, 0 and 1 is 1, which if we then go back and look, 1, 1, 1 is -1. So remember when I said last week, if this doesn't make sense, actually sit and try and do it for yourself a couple times until it does start making sense? Yeah, this is why. It's super unintuitive and doesn't make any sense the first time you think about it, but it actually works out fairly nicely because then everything works. We just add stuff together, just have to mess with our number we're subtracting a little bit. So go back over here. I have built a slightly modified version of the adder that automatically handles subtracting for us a little bit. So same basic idea, except I've added this extra subtract pin, which gets wired into the first carry in input because that's how we handle the whole adding one thing. The subtract is also wired into this 8-bit inverter, which is another little thing I built. Basically, we take 8 bits on a wire, we split them all off, we XOR them with this control bit, because if control is 0, it's just going to pass through whatever the input was originally. If the control is true, then it flips whatever the input is effectively, and then combines them all back up together on one 8-bit wire and sends it back out. So we do that. And then I also used a little doohickey, which is called a tunnel. Basically, instead of having another wire dragging all the way across my circuit, it goes into the tunnel here and comes out the other end. So our carry out output, which is now called overflow, because it indicates that we're trying to do more math than we should be, or we're getting bigger numbers than we should be, is basically the XOR of whether we're subtracting or the carry output of our last adder. So if we go look at this, I currently have the exact same problem we had set up a minute ago. This is 2 minus 3. So the one thing this doesn't do, this doesn't translate the output back into regular people numbers, if you will. So this is still 2's complement encoded, which if you kind of extend what we saw when I was doing the math here, everything being turned on is basically -1. So it still works. We have 2 minus 3 gives us -1. My overflow light is on. I think I have something built incorrectly in here. So that might be homework for you all. Go figure out why my overflow light's turning on when it shouldn't be. So we can do slightly bigger problems. I can go turn the subtract off and prove that adding still actually works, because now I have 2 plus 3, and the result is 5 still, which is good. Do 5 plus 5, which gets us 8 and 2, which is 10. I can do 5 minus 5, which gets us 0, as you would expect. Again, we can go look inside the circuit to go see what's happening. So run our B through the inverter. So everything is turned on except for the 0th bit and the 2nd bit. Then the A is normal. So we actually run through the thing and watch how all the different adders interact with each other to build up our final answer of, nothing. So I have posted links to both go download this software and this file full of these circuits that I've already built up, so you can go play with them yourself. They're, again, posted on the website. So I think that is about it for talking and showing off. What questions do we have? Where are people still confused? Or does everything make sense and you're ready to jump on to the next thing? Cool. So next week, if you thought this was trippy and confusing, next week we're going to talk about circuits that feed back into themselves. So things where the output is wired into their own input, which seems strange and backwards and like it would cause things to explode. But that's actually how we start building like memory and circuits that remember things. So that'll be next week, along with a quick revisiting of how to count this time in hexadecimal, which we already kind of talked about. So it should be a fairly quick, easy read. At least that chapter should be. So I think we're done for this week. Thanks for watching. See you next week.